Ladies and gentlemen, welcome to Fall 22, Test 3 review. Sorry. Here it is. Fall 19 was the exam we took this from. Test 3, Part 4. No labeling on this question. We're going to use a strong acid called HOTS, and once again, they were asked to draw HOTS and show all pi bonds. So you can't just write this. SO3 S, you can't do that. There's pi bonds in there. And you can't say R, you can't do that. But that's a sulfonic acid. Just a little heads up. Drawing out a sulfonic acid is always the same for the sulfur. Looks a lot like sulfuric acid. Then the R for toluene sulfonic acid is a toluene, which is methylbenzene, but it's a group, and it's a para. So it's the methyls as far away from the green as possible. That's what para means. Para toluene sulfonic acid. And it does whatever sulfuric acid does. And this reaction looks like we have the conditions for hydration, except we've replaces HOH with an alcohol. This replaces that. The mechanism is identical. The first step is to protonate the alkyne and make the most stable carbocation, or make both carbocations because there's two products. And I think that's the story. So it's not about just give me the major cation, it's give me both. So we got our arrows. Anybody know what BU stands for? Butyl. And well, we won't have 3 bonds anymore. We'll have 2. And I'll draw the butyl one time just for fun. And the other time I'll just stick with the BU. You can stick with the BU the whole time through. Oh, I like that's catchy. We'll put the plus on the more substituted carbon for one of them and on the less substituted carbon for the other. And that just means the H went on the other position, right? In this one, the H went up here. It's now CH2. Used to be C with 1 H. Still C with 1 H in this one. The new H is here. There was an H. There is an H here. There was not originally. So if this was water, the next step would be attack the cation carbon with an oxygen lone pair. That does not change at all when you switch to an alcohol. Alcohol, here we have 1 propanol. And we're gonna HO propyl lone pair, and we'll do HO propyl lone pair here. Lone pair goes all the way to the C, makes a bond. That's good. The products have a bond from O to C. Make sure that arrow goes all the way to C, please. No, you don't have to mention that at all. In fact, I'll scribble it out. It was just for your information. This is irrelevant. Okay. In terms of your answer, you don't have to put that at all. It's just to jog your memory how to do the mechanism. And we got this green guy, and now it has an oxonium on top. Got an H and a propyl. And this guy, that's that one. And then this guy, he's green up here, and he's got the BU. And an oxonium on top. Hey, blue. Oxonium on top. And it sure looks a lot like that one's going to go up here. Oh, don't lose a half point there. Plus charge. Now I got arrows, not very clear anymore. That goes there, and then this one goes up here. Yeah, but what's going to grab that H? I don't have a base written on my page yet. When you did the first step, what was the other product I didn't show? I got the product that has these carbons in it. OTS minus, very important because that's your base. It's not a great base, but it's the conjugate base of your catalyst. So you need to regenerate your catalyst using that base. And where's the nearest oxonium to this one? Here we go. And there you get your hots back. And you're going to need another hots on this one. So you can just put another OTS here. And neutralize your oxonium there.
Why didn't you attack the first positive carbon with the O?
There was no positive carbon at the beginning. She asked, why didn't I attack the positive carbon with the O at the top? Well, there is no positive carbon until we did step 1. We have to make a cation and then attack it. This is how I did it on the key. Yeah. Yeah. Oh, it's not the same as on the key, or it is the same as on the key? That's the same. I need to look at this key. I'll be right back. That's this one right here. That's this one right here. Yeah.
Are you ready for
See?
that?
Whoa.
Oh, we get
Whoa.
people.
That's on video. That's cool. We almost had a teacher down. Okay. I think what got her, well, got a little back action here. That scared me too. We got a student who's got a little faint over here. I think she didn't see the boo written here, and that threw her off. Because that's what I'm thinking. But she sees it now. And we had a question somewhere else.
Yes.
Yes.
For another problem.
Oh, yeah, we're not quite ready for that. We have to circle our major product, and you got to go back to the cation that's more stable and talk to me about that. And of the two cations, why do I like this first one the best and the second one not as nice? Hyperconjugation. So in B, I'm going to say B starts right here. This cation has more carbocation, right? Oh, it doesn't like when I try to write far left. I told you. Carbocation. Carbocation has more hyperconjugation. So it forms faster. And when I say this, we're talking about this guy right here. Okay. That doesn't look like a good arrow. It's just this one. Put it in now. I think this one. And just to be clear, less hyperconj. You don't need to add the second part, but if I have a comment with the other cation, at least you know which cations I'm comparing. And I believe that would be the circle going to the product that comes from this one, which is that. And that finishes this one. And we're done.